for Chris's talk here. Go ahead and overwrite. And let's see, I think this one, do we need more? Yes, you should select the 3.8 gigabytes of RAM when you start the server. If you have 2, I think it's going to crash. So if you haven't, go to File, Hub Control Panel here, and stop your server, and then restart your server, and then grab a 3.8 gigabyte instance there. Can I go back to where I was? Yeah, I'm here. Okay. And yeah, while you're doing that, I can give a little spiel here. So when we're working with ocean color data, it's easy to kind of think of satellite products as telling us only what's happening right at the surface, and for the most part, that's true. But you know, as we had talked about, what a satellite actually sees is the light that's making it out of the ocean after it's interacting with water particles, dissolved materials below the surface. In other words, you know, ocean color is an integrated signal of how light behaves in essentially the upper water column. But not all light behaves the same way. So some wavelengths penetrate deeper, others kind of disappear really quickly, and how fast that happens depends on how clear or turbid the water is. So this wavelength dependent loss of light with depth plays a huge role in shaping everything from phytoplankton distributions to primary production, and as you know, Chris had showed, even habitat structure as well. So let's slow things down a bit. We're going to just kind of follow the journey of a single photon here, and we'll start by giving light its proper name in this context. Spectral downwelling irradiance just below the sea surface, which we usually write as this sort of ES minus, maybe even you might even see it as ED minus, but either one of these. So for the surface subscript here. So yeah, that just represents the amount of light at each wavelength that crosses the air-sea interface and enters the ocean. So just beneath the water. So once that light is in the water, it begins to fade away. Light is absorbed, it's scattered, and as a result, it decreases exponentially with depth, according to the Beer-Lambert law. And the rate at which this happens is described by the diffuse attenuation coefficient here, or KD. Conveniently for us, PACE offers KD at 17 different wavelengths. So it gives us direct information about how different colors of light are interacting in the ocean. So mathematically, this means if we know the light just below the surface, the attenuation coefficient from PACE, and a depth of interest here, we can calculate how much light of each wavelength is available at that depth. So this is pretty powerful. It means we're no longer limited to thinking in terms of just surface conditions. Instead, we can reconstruct the underwater light field, effectively turning satellite observations into a depth resolved product. And if you're counting dimensions in this case, that's latitude, longitude, wavelength, depth, and time resolutions. That's a 5-dimensional view of light in the ocean, essentially. So if that feels a bit abstract, don't worry. We'll make it into kind of concrete exercises that we'll follow here by building maps and profiles and cross sections, just to kind of show how light actually behaves beneath the surface. So we'll dive on in. All right. If you have been following along, reading my tutorials so far, you'll find it miraculous that there are people on this planet who occasionally take me seriously. I'm too embarrassed to relay my dad jokes to you all in real time here, so I'll just leave you all to cringe in your own time as you reflect on the content. Anyhow, okay. So before we can send light down to the ocean, we need a reference spectrum. So specifically, we need that spectral downwelling irradiance just below the sea surface, that ES term. So this represents the amount of light that each wavelength actually makes, that makes it past the air-sea boundary and into the ocean. So for this tutorial, we're just using a standard reference solar spectrum derived from ASTM G17303 solar reference. It's standard solar reference. Originally computed using a SMARTS version 2.92, apparently. Now, at any given time, any given place on Earth, the solar spectrum actually hitting the ocean, it's subject to change slightly based on your localized cloud cover, as well as changes to solar angles throughout the year. The quantifying can get a little fuzzy when we're talking about like 8-day or monthly averages and spatial binning on top of that. So for our purposes of examining how the light field changes with depth, we're going to go ahead and use this kind of average case scenario. So as I've heard it kind of explained to me before, we're just going to keep our lies internally consistent. So to keep things simple, we've already loaded this reference spectrum into a pandas data frame for you. So it's just our starting rainbow. So that's the light available at the surface before the ocean starts to do what it does best, absorbing and scattering and reshaping it with depth. Again, we assume this average case solar angle and that the light has been diffused by the atmosphere, and then we've lost about 4% of the signal as the water crossed over the air-sea boundary. So anyways, that's all been done. But so yeah, here's our pandas data frame here. Just so this isn't like an abstract concept, let's take a look at what this actually looks like. We're gonna get a little fancy, trying to make a little fancy rainbow coloring here, just to make the idea intuitive. And I like to show little tricks to make aesthetically pleasing plots, because I like that. If you want something more minimal, I included this here. If you're just like, I'm sick of your tips and tricks, Ryan, just here you go, straightforward, plot your wave and attenuation here, and you'll get this black line essentially. Okay. But the nuts and bolts of how to get this, we're basically defining a series of polygons based on four points here: wavelength 1, 0, wavelength 1 end, wavelength 2 end, and then wavelength 2 0. So we're just making a bunch of polygons as we go along through this verts, with the wavelength coming from wave, and then the ES being the second term here. So it's just taking those values and creating polygons. We collect all these and we arrange them according to the colors, which we arranged in a rainbow here, which is how we get it to follow the rainbow. And then on top of it, so we're just adding those polygons. And then on top of that, we add just a basic line plot on top, just to kind of give you an idea of it's kind of coloring each slice by the wavelength just kind of creates a nice continuous rainbow, just showing how each part each color contributes to this total spectrum, I guess. So okay, so let's grab a monthly light attenuation, or KD file. Been through this a few times here. We'll grab a 0.1 degree resolution just to save a little memory here. All right, so let's load up our data set. All right, we have our latitude, longitude, 17 wavelengths. Right. All right, so let's make a little quick plot here. We're going to introduce our coarsening tool again. Even though we're 0.1 degree, we're going to be looking at a big global file here. So the more we sort of coarsen this, the better, the quicker it'll be, at least for demonstration purposes, or if you want to, so anyways, here we're going to choose a single wavelength. This is also something you could do with the remote sensing reflectance as well. This dot select, and you can select a wavelength 490. There's two ways we can do it. At other parts, if I've written these at different times, so I picked up different tricks. In other way, for the reflectance, we've often just said, a wavelength, a defined one, and then define the method as nearest, and it'll grab the nearest wavelength to that. Here, we're kind of doing a different approach, but same basic concept here. Oh no, that's not here. We're just defining 490 here. Here we're just cleaning it just to make sure that we're getting rid of all of our negative values, and then coarsening a little bit. So 490 is kind of a standard reference wavelength for light attenuation. Don't worry, we're going to bring in more wavelengths here, but this is just kind of get a global picture. So the rest of this is just plot formatting and putting things into log scale here. I like to, instead of translating the product into log and then plotting it, I do like to use this this function, which takes which is it? I think it's the oh, here it is, the matplotlib colors log norm, importing that, and it just helps make it so your color bar is log distributed, and you can plot your data just kind of as is. I think it makes for prettier, more interpretable metrics here. Okay, so I'll just put in some little markers here because we're going to refer back to these. A little open ocean and an upwelling region here. It's basically, it's helpful to think of KD in terms of a rate. Lower KD values mean that there's a lower rate of attenuation, so light has a chance to penetrate more deeply into the water column, whereas higher KD values indicate that the light is being absorbed or scattered more quickly, so it doesn't reach as far into the water column. Since we're on a visualization kick here, we did want to demonstrate using HV plots. We can make this a little more interactive. It's RAM efficient because it initially loads a coarsened overview, and then it only fetches the higher resolution data as you zoom in here. So where's this line? HV. What am I looking for here? There is a HV. Oh, that right in front of my face. Okay, this HV extension bokeh here. This tells HV plot which sort of plotting backend to use. In this case, this bokeh is a Python library for creating sort of interactive, web-ready visualization. So it handles zooming and panning, tooltips, and efficient sort of rendering of large data sets here. So I can zoom in and see the various values here, and you kind of see as you zoom in, it takes a second, but it'll change the resolution as you zoom in. So it's not loading all of this sort of all at once, just the part that's being shown here. So no need to transform your data or any extra libraries. That HV extension there just hooks everything together. So your HV plot just calls the work interactively here. So, okay, just cool little fun things you can do. So let's dive a little deeper, kind of see what's going on beneath the surface here. Let's just isolate a pixel within that image. We're going to define a location and then extract an X-array data set using the nearest function that we've seen before. For this particular location. Ian has a really cool update to this in data extraction in the help desk somewhere on the Slack, which is pretty cool. But for now, using this just to select the nearest pixel. So for our reference spectra, you can't use nearest here. So we do the KD, select nearest. Now we want to match the values against this ES select as well, but we can't use the nearest here because as DF ES is a plain data frame, not an X array with coordinates. So instead, we know that the wavelengths are the same, so we can index the data frame by just setting the wavelength column as the index and then selecting those matching values directly. So we can put the exact ES values corresponding to our KD wavelengths. So we're trying to match those up. it's a really small nitpicky detail, but this has just been a source of confusion for me in my journey in Python when just mixing and matching data sets and that are kind of set up differently. It is maybe intuitive to some, but mixing and matching just sometimes gets me confused, and I forget to kind of put them on the same, speaking the same language here. So that's what this is doing. All right, so we're going to define a series of depths, 200 meters, 0 to 200 meters in 2-meter increments. And for each depth, we're going to compute how much light remains at each selected wavelength, which we chose here. There's 3 selected wavelengths. And for each wavelength, we take the surface irradiance, that's ESL, and then we're going to attenuate it exponentially using that corresponding diffuse attenuation coefficient. So using these KD values for pace, we're just attenuating this EO here. So once again, there's kind of a small nuance in mixing data sets here. The ESL comes from a plain data frame, so we can loop over it directly, while KD cell is an X-array object, so we need to access its raw values with dot values here. So again, we've lined them up, but here we got to do KD cell dot values because it's an X-array, where ESL data frame, so we could just call it directly. So let's go ahead and run this. So here we go. We got some vertical profiles of light, diffuse downwelling irradiance, or ED, at these various wavelengths, red, green, and sort of bluish channel. So you can see that light really likes to travel in terms of depth here. We're out in the middle of the ocean here, and attenuation rates are pretty low. So this is what we expect. So green light, blue light goes pretty deep here, almost to 200 meters. Green light does pretty fair job too, and then red light, the little photons that could, they just didn't stick around long. Even in just the cleanest water, pure H2O loves to absorb red, so it taps out pretty quickly. Even in the clearest waters, we're not even getting to 15 meters. So so let's look at this another way. Now that we've got all these extra wavelengths from pace, let's put them to work. So we'll define, instead of doing a depth profile, let's just hold a depth. Let's just define some nominal depths here, and then look at how for each depth, we'll apply our handy light attenuation equation here. And instead of defining only 3 wavelengths, let's keep the whole spectrum, and then we'll just see how it changes with depth. So here is our surface spectrum that we defined at the beginning. Already at 1 meter, you can see that red light starting to disappear. By 10 meters, it's pretty much gone. And you can see in these blue waters, what's remaining is this blue end of the spectrum here. And the deeper you go, you can start seeing some of that green light dissipate. And by the time you're at 100 meters, you're really left with just this sort of 400 to 500 nanometer portion of light. So it's substantially changing sort of the light field, and you can see spectrally how that changes at depth. So yeah, if you want to try to play around here, try switching the coordinates closer to the coast as well that we defined previously up here. Go ahead and put them anywhere you want, and you can kind of see how both of these change for that. All right, how about let's take a little more integrated look, because like right now we've had to kind of hold one thing constant and show the other, try to bring them together so we can really kind of focus on what's happening as light moves through the water. We're going to focus on 2 points, our little open ocean one here, and you'll recall we put another point in that upwelling region. We'll just call coastal coordinate here. It's an upwelling region on the Patagonian shelf. So we'll use the steps we used earlier, but we're going to tweak the data a bit to get higher resolution and depth. Specifically, we'll generate this ED spectrum every 2 meters down to 100 meters. And once we've stacked all that together, we can plot it like a cross section, kind of giving a nice visual of the 4D nature of these paste KD products. So latitude, longitude, there, for select latitude and longitude, wavelength and depth are all in one picture. So most of these sort of tools and tricks are things that we've already used. We're just grabbing our KD values from these two locations that we've defined, grabbing our reference spectrum at the surface, and then defining all the depths we want to propagate our light to, and then proceeding to calculate those light levels at each of those depths. And then we're into sort of plot formatting space here. There's a few little things kind of worth pointing out. First, each wavelength is assigned a color value via this NumPy spectral. Where is it? Where did I put that? Oh yeah, here we go. Yeah. And look at the right part. So this is just the color scale. So you can change this to your jet or preferred color scale. Next, we'll divide our spectra at each depth by the surface value. So there's our surface value. Here's our attenuation at depth. And we divide those to kind of normalize it to the surface. Now we're ratioing it against the surface, and so that converts the depth integrated values from a 0 to 1 scale. So what we then do is simply adjust the intensity of each color with depth by multiplying each color by that 0 to 1 scale. So we've effectively just used paste KD data to help us manipulate the color scale to adjust the colors with depth. That's what we're using. We're using that attenuation to adjust the color scale. Now we can have like a nice cross section of the ocean showing how deep each wavelength goes into the water. I will say, now that we're in relative space, if anyone wants to argue about whether or not our input light attenuation was proper or not, it might change slightly in intensity, different areas, different parts of the year. Right now we're looking at relative changes here. So as a function of percent, as a function of how much light is at the surface. So we're in relative space here. Chris, in some of our discussions pointed out, I'm pretty sure it works this way. I think you could just feed a spectrum of all ones at the surface, and then you basically don't have to normalize it. It kind of it already does that. I think it works as simple as that. I hadn't thought of that before, but anyway, you can notice that the blue light, it barely makes it down in the upwelled waters here, and that's because those greedy little phytoplankton are gobbling it up for photosynthesis, right? And as we've mentioned before, we think of algae as green. They look green to our eyes because they're really just using up nearly all the other wavelengths and just leaving green behind. But on top of that, there's other stuff in the water, the sedum, detritus, which are also absorbing blue light, which changes how fast these sort of colors fade with depth. And remember, attenuation isn't just absorption. Light gets scattered too. It can bounce off particles multiple times. Sometimes that might increase the chance that it's absorbed on its way back up because it's got basically a longer path length. So that single surface reflectance measurement from space is really just the tip of a complex story of light interacting with water, particles, and life beneath the surface here. So, all right, moving on from that. When we think about light underwater, it can be helpful to summarize the total amount of photosynthetically available radiation, or PAR. This is basically the light that phytoplankton can actually use to power photosynthesis. PAR is a cornerstone for primary productivity models because it tells us how much energy is available to fix carbon at any given depth. But it's also handy for thinking about fish vision in general and general light availability underwater, as Chris had mentioned. So PAR itself is defined as basically the sum, or technically the integral of all this usable light across the photosynthetically active wavelength. So that's 400 to 700 nanometers, which we've been kind of interacting in that space most of the time anyway. In plain language, this integral just tells us the total amount of visible light at depth. So Up until now, we've only looked at 1 month, so we're gonna shake things up a little bit and explore all the months of our coastal point just to see how light attenuation changes the underwater light field over time. So we're going to go back and use our nested trick here of concatenating by time. All right, it's still going. Yeah, we're going to use this open MF data set to grab this time series. Open up our metadata. Oh boy, it's still going. All right. Where do I define the time here? Did that disappear from here? I feel like I'm missing something. Oh no, because I'm going to grab the whole. I'm going to grab the whole thing, the whole time series. Okay, because I'm only doing monthly. That's right. Oh, it's taking its sweet time. There we go. Okay, so grab 21. We just grabbed the whole time series, the monthly time series. So there's 21 months available. Got it open. We're going to concatenate by that time dimension. And then we have to define that time coordinate as well, which is kind of irritating, but there it is. All right. So a little extra flair here. We're also going to overlay the climatological mixed layer depth. We talk more about that in a moment here, but we're just going to see how quickly sort of light is fading with depth at a specific location and show that over time. So let's show you the plot first, and then we'll kind of go over what's going on under the hood here. So as before, our goal is to identify the percent of surface PAR levels and track how their depths change over time. So rather than sampling PAR at arbitrarily chosen depths, we can take advantage of the physics encoded in the PACE data itself. So because underwater light attenuates exponentially with depth, it's more physically meaningful to define our target light levels evenly in logarithmic space rather than spacing them linearly. So using a natural logarithms just kind of keeps this formulation consistent with the exponential attenuation equation. So the approach generates 10 sort of reference light levels ranging from 99% of surface PAR down to 1%, and they're evenly spaced in log space based off of the depth, based off of the KD values essentially. So each step therefore represents an equal fractional decrease in light, not an equal absolute decrease. Exactly how. So it's more like how light is behaving in the ocean. So in practice, this means that we're letting the light field tell us where the important depths are rather than prescribing them a priori like we have been along the way. So for each step, we compute the full vertical profile of PAR by integrating the spectral downwelling irradiance from 400 to 700 nanometers at every depth. We could actually also grab the PAR products already pre-computed through PACE as well. But we've done some comparisons. You end up at a pretty very similar answer, but the PAR products are probably more accurate in taking into account those changes with solar angles and whatnot. So then we normalize this profile by its surface value and identify the depth at which PAR drops to each of our predefined fractions. So 99%, 60%, 35%, down all the way down to 1%. So using those indices, we just extract the corresponding depths and then track how these sort of characteristic light levels evolve through time. And we loop through and do this for every available month. And now we have this cool time series here. So So this plot shows the depths at which different fractions of surface par remain over time. So the lowest dot in each month represents the 1% par level, which is commonly used as an estimate of the euphotic depth. You might see ZEU. So this is the euphotic depth at which light becomes limiting for photosynthesis here. And then we overlaid this climatological mixed layer depth in here to provide some context on kind of the local hydrography and highlight the relationship between light availability and vertical mixing. So when the ZEU here, when our euphotic depth is below the mixed layer depth, we've got a well-lit portion of the water column that extends below the mixed layer. So you still have light underneath the mixed layer. This allows phytoplankton access to nutrients that are entrained from deeper waters while receiving sufficient light that they can still do photosynthesis down here. So this, we can get some subsurface chlorophyll blooms, and you can get a lot of photosynthetic activity kind of happening well below the surface. When our euphotic depth is greater than the mixed layer depth, the entire mixed layer is sort of illuminated, or maybe in some cases the light didn't really get down to the mixed layer, but the nutrient resupply from below is reduced. So if you're a phytoplankton hanging out here, you're kind of still you're recycling nutrients in the surface layer here. You don't have access to some of those deep nutrients. So that kind of switches over. Now you're making nutrient availability rather than light, kind of the dominant constraint on phytoplankton growth. So, together these metrics illustrate how the kind of interplay between light attenuation and mixing controls primary productivity at this location and over a seasonal cycle. This could also determine how much carbon is being recycled, how much carbon is available for little grazing zooplankton to munch on and then feed the fish. Some productivity models, including the CAFE model that PACE will soon be distributing, actually uses this information and parameterizes their models differently depending on where light is in the water column relative to the mixed layer depth. So, all right, one last little exercise with light. So in this example, we integrated the spectral signal to get PAR, or basically a metric of total light availability. To dig back into the spectral structure of the underwater light field, we'll modify our perspective slightly. Here for each individual wavelength, we'll find the depth at which that one wavelength's downwelling irradiance has dropped to 1% of its surface level. So not all of PAR, just each wavelength's 1% surface value. Then we'll repeat this for every wavelength every month using the PACE-derived KD values. So we're kind of doing what we did in the last plot, but instead of calculating the 1% PAR, we're looking at this for each individual wavelength over time. So in the figure, the x-axis here is the wavelength, and then the y-axis is the depth of the 1% light level at each wavelength here. And each of these different lines are color coded according to a different month. So we're looking at a time series sort of based on this legend here. So the wavelengths that appear deeper on the plot are those that penetrate further into the water column before being attenuated. And then you can see seasonal shifts in these curves that reflect changes in water clarity, total water clarity, and then composition, such as phytoplankton biomass or CDOM, particle loads, so that sort of differently absorb and scatter light across the spectrum, and sort of change that balance of how much what type of light is available. So taken together, this view kind of highlights how the spectral window, I guess, of usable light changes, and why hyperspectral products like PACE, KD allow us to move beyond bulk light metrics and really examine the physical and biological controls on underwater light penetration in much finer detail. Before this, we were typically just looking at 490 alone as a single wavelength for global studies. So resolving how this full spectrum of light kind of evolves with depth, with season, and water type really kind of gives us more physically grounded insights into primary productivity, habitat structure, ecosystem function, and as Chris mentioned, even fish vision. So go PACE, hopefully this notebook has to spark some ideas about how light availability itself can be treated as a very rich, as having very rich environmental information, not just an intermediate step into another product. It's a pretty powerful one in itself. So stop there if anyone has any questions.